In the last video, we talked about the Gaussian distribution. In this video, let's apply that to develop an anomaly detection algorithm. Let's say that we have an unlabeled training set of m examples, and each of these examples is going to be a feature in Rn. So your training set could be m feature vectors from the last m aircraft engines that you manufactured, or it could be features from m users or something else. The way we're going to address anomaly detection is we're going to model p of x from this data set. So we'll try to figure out what are high probability features and what are low probability types of features. So x is a vector, and what we're going to do is model p of x as probability of x1, that is of the first component of x, times the probability of x2, so probability of the second feature, times the probability of the third feature, and so on, up to the probability of the final feature xn. I'm leaving space here because I'll fill in something in a minute. So how do we model each of these terms, p of x1, p of x2, and so on? What we're going to do is assume that the feature x1 is distributed according to a Gaussian distribution with some mean, which I'm going to write as mu1, and some variance, which I'm going to write as sigma squared 1. And so p of x1 is going to be a Gaussian probability distribution with mean mu1 and variance sigma squared 1. And similarly, I'm going to assume that x2 is distributed Gaussian. That's what this little tilde stands for. That means distributed. It's distributed Gaussian with mean mu2 and sigma squared 2. So it's distributed according to a different Gaussian, which has a different set of parameters, mu2 sigma squared 2. And similarly, x3 is yet another Gaussian, and so this can have a different mean and a different standard deviation than the other features, and so on up to xn. And so that's my model. Just as a side comment for those of you that are experts in statistics, it turns out that this equation that I just wrote out actually corresponds to an independence assumption on the values of the features x1 through xn. But in practice, it turns out that the algorithm I'm going to describe, it works just fine whether or not these features are anywhere close to independence. And even if independence assumption doesn't hold true, this algorithm works just fine. But in case you don't know those terms I just used, independence assumptions and so on, don't worry about it. You'll be able to understand and implement this algorithm just fine. And that comment was really meant only for the experts in statistics. And finally, in order to wrap this up, let me take this expression and write it a little bit more compactly. So I'm going to write this is a product from j equals 1 through n of p of xj parameterized by mu j comma sigma squared j. So this funny symbol here, this is actually a capital Greek alphabet pi. That funny symbol there corresponds to taking the product of a set of values. And so, you're familiar with the summation notation. So if I write sum from I equals 1 through n, of I, this means 1 plus 2 plus 3 plus dot 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 up to n. Whereas this funny symbol here, this product symbol, right, product from I equals 1 through n of I, then this means that it's just like summation, except that we're now multiplying. So this becomes 1 times 2 times 3 times dot 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 up to n. And so using this product notation, this product from j equals 1 through n of this expression, that's just a more compact, or like a shorter way of writing out this huge product of all of these terms up there. Since we're taking these p of xj given mu j comma sigma squared j terms and we're multiplying them together. And by the way, the problem of estimating this distribution p of x is sometimes called the problem of density estimation, so hence the title of the slide. So putting everything together, here's our anomaly detection algorithm. The first step is to choose features or come up with features xi that we think might be indicative of anomalous examples. So what I mean by that is try to come up with features so that when there's an unusual user in your system that may be doing fraudulent things, or when, for the aircraft engine example, when there's something funny, something strange about one of the aircraft engines, choose features xi that you think might take on unusually large values or unusually small values for what an anomalous example might look like. But more generally, just try to choose features that describe what you think that describe general properties of the things that you're collecting data on. Next, given a training set of m unlabeled examples, so x1 through xm, we then fit the parameters mu1 through mu_n and sigma squared 1 through sigma squared n. And so these were the formulas similar to the formulas we had in the previous video that we're going to use to estimate each of these parameters. And just to give some interpretation, mu j, that's my average value of the j feature, right? So mu j goes in this term p of xj, which is parameterized by mu j and sigma squared j. And so this says, for the mu j, just take the mean over my training set of the values of the j feature. And I just mentioned that you do this, you compute these formulas for j equals 1 through n. So you use these formulas to estimate mu1, to estimate mu2, and so on up to mu_n, and similarly for sigma squared. And it's also possible to come up with vectorized versions of these. So if you think of mu as a vector, so if mu is a vector, that's mu1, mu2, down to mu_n, then a vectorized version of that set of parameters can be written like so: sum from I equals 1 through m xi. And so this formula that I just wrote out estimates, where these xi are the feature vectors, this estimates mu for all the values of n simultaneously. And it's also possible to come up with a vectorized formula for estimating sigma squared j. Finally, when you're given a new example, so when you have a new aircraft engine and you want to know, is this aircraft engine anomalous? What we need to do is then compute p of x. What's the probability of this new example? So p of x is equal to this product, and what you implement, what you compute, is this formula. And where over here, this thing here is just the formula for the Gaussian probability. And so you compute this thing, and finally, if this probability is very small, you then flag this thing as an anomaly. Here's an example of an application of this method. Let's say we have this data set that I've plotted on the upper left of this slide. If you look at this, well, let's look at the features of x1. If you look at this data set, it looks like on average, the features x1 has a mean of about 5, and the standard deviation, if you look at just the x1 values of this data set, it has a standard deviation of maybe 2, so that's sigma 1. And looks like the x2, the values of the features as measured on the vertical axis, it looks like that has an average value of about 3 and a standard deviation of about 1. So if you take this data set and if you estimate mu1, mu2, sigma 1, sigma 2, this is what you get. And again, I'm writing sigma here, thinking of standard deviations, but the formula on the previous slide actually gave estimates for the squares of these things, right? So sigma squared 1 and sigma squared 2. So just be careful whether you're using sigma 1, sigma 2, or sigma squared 1 or sigma squared 2. So sigma squared 1, of course, would be equal to 4, for example, as a square of 2. And in pictures, what p of x1 parameterized by mu1 and sigma squared 1, and p of x2 parameterized by mu2 and sigma squared 2, that would look like these two distributions over here. And it turns out that if you were to plot p of x, right, which is the product of these two things, you can actually get a surface plot that looks like this. So this is a plot of p of x, where the height above this, where the height of this surface at a particular point. So given a particular x1, x2 values of if x1 equals 2, x2 equals 2, that's this point, and the height of this 3D surface here, that's p of x. So p of x, that is the height of this plot. This is literally just p of x1 parameterized by mu1 sigma squared 1 times p of x2 parameterized by mu2 sigma squared 2. Now, so this is how we fit the parameters to this data. Let's say we have a couple new examples. Maybe I have a new example there. Is this an anomaly or not? Or maybe I have a different example. Maybe I have a second example over there. So is that an anomaly or not? The way we do that is, well, we would set some value for epsilon. Let's say I've chosen epsilon equals 0.02. I'll say later how we choose epsilon. But let's take this first example. Let me call this example x1 test. And let me call the second example, x2 test. What we do is we then compute p of x1 test. So we use this formula to compute it, and this looks like a pretty large value. In particular, this is greater than or greater than or equal to epsilon, and so there's a pretty high probability, at least bigger than epsilon, so we'll say that x1 test is not an anomaly. Whereas if you compute p of x2 test, well, that gives a much smaller value, so this is less than epsilon, and so we'll say that that is indeed an anomaly because it's much smaller than that epsilon that we chose. And in fact, I'd improve it here. What this is really saying is that if you look at this 3D surface plot, it's saying that all the values of x1 and x2 that have a high height above the surface corresponds to a non-anomalous or sort of an okay or normal example, whereas all the points far out here, all the points out here, all those points have very low probability, and so we're going to flag those points as anomalous, and so it's going to define some region that maybe looks like this, so that everything outside this it flags as anomalous, whereas the things inside this ellipse I just drew, if it considers okay or non-anomalous, not anomalous examples. And so this example, x2 test, lies outside that region, so it has very small probability, and so we consider it an anomalous example. In this video, we talked about how to estimate p of x, the probability of x, for the purpose of developing an anomaly detection algorithm. And in this video, we also stepped through an entire process of getting a data set, fitting the parameters, doing parameter estimation to get mu and sigma parameters, and then taking new examples and deciding if the new examples are anomalous or not. In the next few videos, we'll delve deeper into this algorithm and talk a bit more about how to actually get this to work well.